So let's calculate the induced charges in depletion and inversion. Okay, so you've seen the sketch of the total charge in the semiconductor as a function of the surface potential psi s before. So let me go into detail where these curves come from, especially why is this shooting up like an exponential. We had just derived from a depletion approximation this expression here, where this goes as square root of s, and then the gate voltage goes as linear as psi s. Now, this is plotting the total charge. This is not plotting the potential that is dropping across. And that's a big difference, and we'll talk about the relationship between the gate potential and the charge in the system. This is different than the surface potential, and we'll see how that works out. So psi f, as opposed to psi s, is the distance between EF and the intrinsic EF. Okay, so that's the EF here at the interface versus the intrinsic EF. All right. Now, we will define this point here as 2 phi f. And at that point, let's leave it at that. When you have this turnover here from going square root to the exponential, that is the term we coin 2 phi f. And we'll go into detail why we call it 2 phi f in a second. The key element that you need to realize in these derivations, or that's where we're aiming for, is that it's going to be very hard to ramp up your psi s beyond the 2 phi f. Okay? So, and we'll get into details why that is, but you'll get some intuition why. And it basically has to do with the electrons being piled here directly at this interface. And you can pile a lot of electrons into this triangular notch here with very little potential difference. So with very little surface potential difference, you can ramp up your occupation of states rather dramatically. This is different from basically extending out your depletion region out here as a function of psi s. Okay? So in one region it goes as square root of psi, in the other region it goes exponential as psi. And that has to do with how the carriers are being distributed in space and how they depend on the surface potential against the Fermi level in the system. All right. Okay. So let's ask now, what happens when the surface potential is 2 phi f? Okay, so we're just taking the same expression and we're plugging in the applied voltage when psi s is 2 phi f. Okay, what does that mean? We're going to look at the number of electrons in the system. We have done this before. We looked at the electron distribution when we calculated Shockley-Reed-Hall distributions. We defined number of electrons as Ni times the intrinsic level at the surface minus the Fermi energy. Okay. Now, I can expand this out to be inclusive now, including the bulk as a reference. Okay, so I just added and I divided by the exponential and multiplied by the same exponential. But now I can capture this where I have the EI bulk and the EIS are being captured, and I capture my difference in the Fermi levels here in this phi f. Okay? So now I can represent the electron density at this level of a surface potential 2 phi f. Okay, and that happens to be exactly the acceptor doping. So we define threshold by the point where the number of inverted electrons that is going to grow here is identical to the number of exposed donors. Okay? That is how we define 2 phi f. That's the surface potential when that happens. So that's the point at threshold where the number of inverted electrons that are sitting up here is becoming identical in amplitude locally to the acceptor level. Okay? That means threshold. What does that mean intuitively? This is when we're starting to build a significant amount of electrons in the inversion layer. Okay? And that means, okay, here's electron concentration equals the background acceptor concentration. But what does that mean? So in that time, at that point, the green bar is becoming more and more important compared to the red bar. And above threshold, you can pile up electrons at that interface with an exponential potential dependence. Okay, remember, when the Fermi level here is getting closer to the conduction band, a small change of that Fermi level against the conduction band level can have an exponential growth in charges. Okay? Again, that's similar to this. If you can bring the Fermi level close to the conduction band, that's when you have a lot of charge. Okay? That means we can pile up a lot of charge in the interface. And what that means is, when we have a potential here, that most of the potential will now fall over the oxide. Because we just need to wiggle this potential here slightly and get a ton more charge. That means we have to pull really hard here electrostatically just to move this ever so slightly. Okay? And that's where we'll see some interesting math in the next segments. Okay? Now, let's talk a little bit about scaling and the meaning of threshold and what we're trying to do. So if you want to operate a MOSFET, you want to operate it such that you have operation here in this inversion charge. So you need to have a lot of electrons in your inversion channel. Okay? So you need to have an operation above threshold in general. Okay? So you need to get carriers into the channel. But the operation of the circuitry goes as the square of the applied voltage. Okay? So it goes at least the square of the threshold if that's your minimum voltage you apply, and you typically need to apply more than that, right? Because you're operating above threshold. Okay? So that means you would like to reduce the threshold voltage. Now let's look at how we define the threshold voltage here, right? How do you reduce this term? Okay? This is the oxide thickness. You can reduce the oxide thickness. Okay? And that is what people have done. They have reduced the oxide thickness from 1,000 angstrom in the 1970s to about 10 angstroms now. 10 angstroms. You know how many atoms that is? It's about 5 atom layers. Okay? Very, very thin. And you do this in a wafer, maybe a 12-inch wafer in mass production. You know how that translates? It's like you cover the US in snow to 6 inches, and it's perfectly flat. The whole US, 6 inches, no deviation. That's how hard it is to do this. And it is implemented. People do this. I mean, in companies that mass manufacture these devices do this every day, every hour. So, what else can you do? You can't, well, the point is you can't make it much smaller because you will have tunneling through the gate. So the device will be leaky. We'll talk about that in a little bit. What else can you do? You can reduce the oxide dielectric here, or you have it in the, denominator. So you increase the oxide dielectric, okay? That's called, people talk about high K dielectrics, and hafnium oxide is one of those. So typically we had silicon, and now we have high K dielectrics that reduce the threshold voltage, okay? All right. So now let's look at the charges below threshold still, okay? This is the same expression as what we had before. We can express it as the surface potential, and it's some coefficient B. Okay, so it grows exponentially as we have. It becomes really only relevant once this potential gets close to the conduction band edge there. Okay? All right. Now let's integrate the charge in the system and get a feeling to how the gate potential relates to the surface potential. Okay, so this looks very much like a triangular potential well, which means you have a constant electric field, and you have the acceptor charge that's in the depletion region approximation is, or looks like that's like a square, and you can imagine that you will have an exponentially distributed charge of free carriers, inversion carriers that are sitting in the inversion channel. That's plotted in green. We're going to approximate this, since it's really an exponential, by almost like a sheet charge, right? We'll call this green a sheet charge that is in a very small dimension of a few angstroms. That's how narrowly confined the charge will be. All right, so let's see if we can calculate the charge in the channel above threshold, okay? So we would have to, well, if we want to integrate or obtain the charge, we integrate it over the distance x, call this distance x here, and we go from the interface to infinity, and we have an expression as a function of our psi x, okay? Nothing new here, same expressions as what we had before. So let's do a slight change of variables. Number one, we assume that Ni is constant and the doping is constant. And we do a change of variables here where we now include the electric field. Okay? And we assume that there is an electric field that is modulating psi, the surface potential. Okay? Now, we should integrate this from psi 0 to psi infinity, but we can also approximate this over a certain region, okay? We'll approximate the electric field over the region where the charge is accumulating like this. Now, if you do that and consider this integral here, you see that you can pull out kT over Q, which it turns out to be a voltage. Here you have an average electric field. That is basically the width of your inversion charge, okay? So that's this width of the green area here, times some charge density that is in that inversion layer, okay? So let's calculate these in more detail. The charge is above threshold. Let's assume, again, there's no charge in the oxide, so that means the potential here drops linearly, field is constant, and if there's no charge in the oxide, you can write down the different potentials, okay? So we know what the electric field in the oxide is. It is the field in a parallel plate capacitor where you take the total charge dropping over a dielectric and a distance x, okay? So just plain parallel plate capacitor, okay? Nothing fancy there. And let's write this down now in terms of our definition of threshold, okay? We said threshold means we have our surface potential psi s to be 2 phi f, okay? So all we're doing is we're substituting the surface potential with 2 phi f, okay? Just follow me. All we're doing is defining threshold when we want to build a difference between the gate voltage and the threshold voltage. Okay? So we're going to build a difference here between those two voltages. Again, threshold voltage means we're just about to turn on all the inversion charges that will all pile up here at the interface. So in threshold means it's just the same as the acceptor doping. Now we're beginning to pile this up. And we define that voltage as that transition point. Okay, at that transition point, we will see that the increase that you can get between these two potentials, psi S and phi F, will be very small. And follow me, we will neglect this term for now. And also the blue region is very thin, but the height is increasing exponentially. So we can neglect this term. And we end up beautifully in this expression where the internal charge is now just dropping off over the oxide capacitance, which is just X0 over kappa OX, epsilon 0, okay? Okay, that's our oxide 1 over C, right? Like that, okay? So, the point is that the charge separation that we have here is now completely just determined by the oxide thickness. There's no charge in the oxide, and we basically have infinitely thin oxide plates, okay? We no longer have a widely distributed charge. So we can pile up exponentially large charge directly against the interface. So really now all the potential that you're going to drop here in the by the gate is going to pretty much drop here over the oxide. So a tiny little bit of wiggle will translate here on this side in an exponential growth of charge. So the additional potential drop will be minuscule. So you can barely get psi S over to phi F, okay? All right, so how can we get this linear charge buildup above threshold? So again, small changes in psi S in inversion change the charge a lot, okay? And that translates then into electric field changes that are dropping across the oxide. So most of the work you do of pulling this down will translate into your lever arm going down and down with very little action on the inversion layer. Okay. So it's like like I said, a parallel capacitor. Now, what happens if you pull this down like this and you get into inversion? You will have some tunneling current. Okay. How do we calculate tunneling currents? Well, we've done this before with thermionic emission, where we have two components, semiconductor to gate and gate to semiconductor. And we have semiconductor to gate is here, we have a charge in the semiconductor here in green, and we have carrier injection from the left, from the metal. They both see this exponential term here in delta EC, and they operate at a thermal velocity, okay? So we can build out this difference between the two terms, and you can identify this, say, with a tunneling coefficient, which is going to be minuscule, like this, if your barrier is big enough, okay? Because the barrier is so high. So that would be thermionic emission over the barrier, and that's negligible. But if you make this thin, then we've calculated tunneling through barriers in the early sections of this course. If significant current flow through this. And therefore, you can have significantly tunneling out of this device. And that is why you don't build these oxides too thin. Okay, so here's a model that shows and experiments that show this, and I'll touch more about that in the next segment as well. So the oxide can't be too thin because of tunneling current. And I guess the point here is also it starts to look like base current in a BJT that you're losing, right? All right, so we got the induced charges, and now we're going to do the exact model, which calculates the psi s and 2 phi f in more detail. Okay, so that's going to be in the next segment.